Okay, for today's meetup, we're going to talk about data engineering with respect to LLMs. We're going to cover three core concepts, and those three core concepts indicate that somebody building the Hugging Face API is working from their MacBook and they're not working on a cluster. So to build an LLM, you'll require some data engineering skills, and it's best to demonstrate that by an API. And the API that we have access to, at least what the Hugging Face API is, there's some good things and bad things. The bad things is that it's not cluster aware. And so what are these three issues? So let's look at the smallest model that we're going to attempt to reproduce. And the smallest model is something called small model. It's 135 million parameters. And the data that they use to build it is called small corpus. It's at this URL here. And at that URL, they show you that there's three different data sets that they use to build that. It's 236 million rows, and there's three text data sets. One is some kind of text corpus. Another one is from universities, which is deduplicated. And the third one is from the Python archive called Software Heritage. So how much is the Software Heritage data set? So the whole thing is roughly 680 gig. And if we figure out how many rows roughly is our Python, it's about 15%, which is about 100 gig. So the warning sign that you have is that when they show you how to debug the Python code, how to download the Python code at 100 gig, there's a warning that says that it takes about 6 hours to download the files. It's just a script that they threw up. Now, we'll need something like this, or we'll have to build an API because we're going to download lots of data, right? And so 6 hours to download 100 gig, it's a little fishy. Something doesn't sound right. So how do we get to the bottom of this? So the first issue is let's figure out what the blob IDs are. So if the blob IDs are, we can try to figure out what content it's downloading from S3. And so before we do that, let's back up a step. So in this code that they're running to download data, they're running 16 streams or 16 threads. I'm assuming that this this AWS instance has 16 cores, right? So 16 cores, what they're doing is they're putting one stream on each core. Now, one CPU core can support multiple streams, and the concept that we're trying to make clear is the issue between I/O bound and compute bound. So what you want to do is get to a point where you're not compute bound. You want to use up the full capacity of the I/O network. And how do you measure that? So you measure that. They provide this TQDM display, which shows you how many examples per second that they're downloading. So if you set it to 16, you'll get around 300 examples per second. If you increase this to 32 or 64 or 128, you'll get up to 1,000 to 1,500. So I think 128 gets up to 1,500. Don't remember exactly. But the issue is that I always adjust your parameters so that you're I/O bound and you're not CPU bound. So at 16, they're still CPU bound. And so the issue between tuning between CPU bound and I/O bound, you could adjust that by sending test traffic through your network and getting that dynamic parameter to be optimal, and then using that in a long-lived download. That's concept number one, I/O between I/O bound versus CPU bound. What's concept number two? So concept number two is a duplicate issue. So when you get all the refs downloaded and you go through those, you can figure out that you're downloading about 2 times the amount of data necessary. And so there's about 15 million records, whereas if you do deduplicate them, there's about 7.6 million, which corresponds to the number of rows that they're advertising on their data set. So this automatically cuts your download time in half, right? So if we can reduce our data set by download times by half here and reduce our data set download by a factor of 4 here, then we're making significant savings, and those should go into an API where you're downloading data. What's the third conceptual issue? So the third conceptual issue is actually a bigger issue, and so this is a very common mistake. So when you're downloading data to your notebook, you're going over the public internet. When you're downloading data between S3 buckets, a common mistake is to use the public WAN or wide area network. So the public WAN is typically can be 1 gig. I don't know for sure, but let's assume it's 1 gig. And so whereas the internal network can be assumed to be 10 gig. Maybe it's 10 times faster. Maybe the difference is even bigger. But the issue is that when you're downloading from S3 bucket to S3 bucket, you have to use a different API. You can't just download through the public API or the public internet. You have to go through the internal. So that should be built into your internet, into your API, right? So to do that in AWS, you have to go. One way is to go through something called AWS Data Sync. And so these are the notes for setting up something for AWS Data Sync. Unfortunately, it wasn't well documented. At least I couldn't find any examples. So I had to kind of figure this out by trial and error. And the first step is to get this working by the AWS console. The second step is to get this working through Boto 3 and to stub it out into an API. And we'll discuss that as we evolve the API over the next couple of weeks or next couple of months. Okay, that's the end for our update for the 26th. And then next week we'll continue with some other topics.